thank you. Our first presentation will be by Rachana Patel from Harvard University, and our presentation will be on the use of explainable AI to refine artificial immune system algorithms. So if you could share your screen, Rachana.
Yes, can you see my screen?
Yes. So as in the previous presentations, you have 20 minutes. You try to allow about 5 minutes for questions. All right.
Thank you very much. First of all, I'd like to thank for the opportunity for me presenting this position paper. And I'm going to talk about use of explainable AI to refine artificial immune system algorithms. Real world data is pretty much has a couple of characteristics, data imbalance and ambiguity. Imbalanced data means within the data set, there is skewed number of samples in particular classes, and ambiguous data means some data samples can be classed into multiple class types. And some of the examples include cancer diagnosis, where most of the samples are normal and benign, and some of them can be malignant. Faulty device production in a production unit, where most of the devices are good, but there can be some devices with bad performance. And the classic credit card fraud example, where most of the transactions will be acceptable, but there will be some unacceptable transactions. And artificial immune system algorithms can be used to actually segregate these data efficiently. So artificial immune system algorithms is a branch of bio-inspired computation for developing computer models and methodologies based on the principles of biological immune system. Biological immune system has a lot of molecular players, and it is body's immune system that can be divided into innate immune system and adaptive immune system. So innate immune system is basically deals with identification of foreign entities within the body and eliminating them, whereas adaptive immunity is associated with memory associated with a presence of antigen. And one of the applications that we are all experiencing right now is vaccinations. So the key attribute of biological inspired computation, which has been exploited by artificial immune system, is the differentiation between self and non-self samples. The negative selection algorithm is a classic AIS algorithm where the NSA classifier is trained by self-samples. So within a data set, any data class can be identified as self-samples. And based on these set of detectors, which are called as T detectors, are created. These T detectors do not match the self-samples, and hence these detectors can be used to identify the abnormal or non-self samples. Now, there are a couple of major caveats of artificial immune system algorithms, including the negative selection algorithms, and these are low interpretability and high false positive rates. So the solutions, which are obvious since morning, are to address the low interpretability. We can use model agnostic explainable AI algorithms like Lime and Sharp to identify the deterministic features and following explanations, and to reduce the high positive, false positive rates. Various AIS algorithms can be hybridized or can be refined. So what we are proposing is, if we combine the two, we can use explainable AI algorithms to refine the AIS classifiers. One of the algorithms that was proposed by Das Gupta in 2009 to refine NSA is a conserved self-pattern recognition algorithm. Now, since NSA, that is negative selection algorithm, uses one class, which is self, to train, the false positive error rate is high. And one can imagine that this error rate will be further exaggerated due to class imbalance within the data set. So for this, the chist-era algorithm was created, which is inspired based on the danger theory of biological inspired immune system. or biological immune system. So the danger theory suggests that there are two parallel lines of defense in the body. The one line is the T cells that we have already seen in negative selection algorithm that pretty much differentiates between the self and non-self. And the other aspect is antigen presenting cells, which are molecular players of biological immune system, which do pattern recognitions. So the AIS algorithms that are inspired from these biological immune systems include APC detectors that recognize self patterns and T detectors that recognize non-self patterns. And these together creates this conserved self pattern recognition algorithm. So if we go a little bit detail into this, we see that the initial aspect is same as negative selection algorithms, where we use self-samples within our data set to generate T detectors that will detect the non-self samples in the test data set. The second aspect of this algorithm is creating APC detectors, which is by identifying the self patterns which are present within the data set. And this can be done by using either the classic correlation analysis approach, where we identify features that correlate strongly with the self class, but do not correlate with each other. Alternatively, we can use XAI algorithms like LIME and SHARP to identify the deterministic features that are responsible for this data segregation. And these APC detectors can be then used to confirm the self samples. So thereby we can decrease the false positive rates. Now, the question is, how are we going to select these self patterns, right? Now, as I mentioned before, the pattern selection we can do by a classic approach of correlation analysis, or what we are proposing is by using LIME and SHARP. So here I've given an example of cancer diagnosis, which is an output through LIME. Now you can see that this is a binary classification where there is either malignant sample or benign sample, where let us consider benign as self. So if this is the case, then there are a couple of features that we can see are associated with benign classification. So we can identify such features through different algorithms, which can be associated with self data sets or self samples. Obvious potential problems for this is there will be different features that will be identified by each of this analysis, and hence there will be minimal overlap. So the potential solutions for this can be two things. One is if there are common features that are identified between all three of these approaches, then we use them. And if not, then we just use cumulative features. So we just aggregate all the features from all of this to create APC detectors. Now, the CSP-RA algorithm uses only self patterns, but we can further refine this algorithm by also using non-self patterns. So one of the problems with this hybrid algorithm of NSA and CSP-RA is the classifier is trained only with one class, that is self class. So we can employ a refinement where we can use both self and non-self patterns to train the algorithm. And this is inspired by danger theory of self and non-self, of safe or danger signals, which are pretty much carried out by dendritic cells, and hence this algorithm is called dendritic cell algorithm. So dendritic cells can differentiate into three different forms. The immature dendritic cells, which pretty much are going to do the self, non-self differentiation. The semi-mature dendritic cells are generated when they encounter safe signals. Safe signals are nothing but self patterns. And mature dendritic cells are formed when they encounter danger signals, and danger signals are nothing but non-self patterns. So as you can see from this, we can generate a artificial immune system algorithm, which is the dendritic cell algorithm. So overall, the proposed classifier pipeline is something that looks like this. where the data sets will be first exposed to first hybrid algorithm that will be a combination of negative selection algorithm with T-cell detectors, which will detect the non-self samples. The CSPRA and APC detectors will confirm the sample as self or non-self. And this can be achieved by combining the XAI algorithms with correlation analysis. This pipeline can be further refined by adding the dendritic cell algorithm into the mix, which will further take into account both the self patterns as well as non-self patterns to then finally segregate the samples into either acceptable data or unacceptable data. The way this classifier pipeline is designed is each of the AIS algorithm tries to mitigate the caveat of the previous algorithm, and we are planning to use explainable AI for these kind of refinements. And with this, I would like to acknowledge Bai Peng, who is my academic supervisor, and for all his support and helpful discussions. My friend Peter, who helped me with the presentation, and Data Labs for supporting my studies. Thank you very much, and I'll take questions.
Thanks, Rachana, for that interesting presentation. If you have any questions, please raise your hand and ask away. Well, while others are preparing their questions, I have a quick one. You mentioned the mature and immature regarding the that DCA. Could you shed more light on that? I didn't quite get how it fits into it and the decision making in the last diagram that you showed.
Right. So the idea is like the dendritic cells. So if you have a set of samples, we will be using the self as well as non-self patterns, because till now we are using only self patterns. So if we create a detector that can detect also the non-self patterns, so it will almost be like when the samples which match the defined non-self pattern, then the sample is considered as a danger sample, and the dendritic cell that we create in our algorithm will be converted to a mature dendritic cell. So the output will be what kind of maturation level we will get, which will be a rule-based stuff. And we can also, like an additional thing which I didn't mention is we can refine this further to combat ambiguity by adding fuzzy logic into it. So we can define our own rules of when the dendritic cell is going to mature or how it is going to mature. But this maturity will be based on the self patterns or non-self patterns, which are predetermined.
Okay, yeah, thanks for that. Yeah, another question yet. I'll just ask a quick second one. Looking through the paper, you mentioned two possible challenges or limitations in the idea regarding generalizability and coverage. Could you shed more light on those challenges, and which of them do you think will pose a greater challenge?
So yes, generalizability might be an issue, but I suppose we will have to from the limited experience that I have with these algorithms, I think the generalization might be an issue, but with appropriate feature selection, that can be mitigated. And I think that will automatically help the interpretation. So if we bring down the features to a list of 4 features, for example, if my data set right now has 99 features, and if I bring it down to 4 or 5 deterministic features, then that can be generalizable, because a similar data set might have similar features. And then the the variables will reduce.
Yeah. Okay. Yeah, I think that highlights the importance, the way you combine the features from the two explainers. So I think that will play an important role in kind of determining what features you end up with and how generalizable they could be.
Yes, I think that is something I'm looking forward to, because it's not something that I'm actually right now. I'm not sure what it will be. Like it can, if I'm lucky, I'll find, or if the data set is good. It's nothing to do with my luck. It's pretty much about the data set. So if there are some deterministic features which are standing out, then there will be a good overlap. Then the decision making will be pretty straightforward. However, if that is not the case, and if I find mutually exclusive features in each of the explanations, then that will be a problem, because the entire idea is to reduce the features and not to compile another little data set. Yeah. So that, I mean, but I guess it will be a trial and error. As long as we can improve the accuracy and decrease false positive, I think we will be achieving our goal.
Yeah. Yeah, I agree. So thanks for that, Rachana. I think we'll go to the next paper now.
Thank you very much.
Yeah, thanks. So our second position paper is by Martin Fyvie from Robert Gordon University, and it's on non-deterministic solvers and explainable AI through trajectory mining. Martin, if you can share your screen.
Yep, of course.
Thank you.
Sorry, just to check, is my screen up?
No, it's not up yet.
Oh.
Okay.
Perfect. Yes, my name is Martin Fyvie, and I'm here at the Robert Gordon University, and I'm just going to quickly cover a position paper that I entered as into non-deterministic solvers and how it fits in with explainable AI through specifically trajectory mining, which is a PhD project which I've recently started on, and so I'd like to just introduce the concept. So non-deterministic algorithms themselves, within this talk, what I mean by that is algorithms that tend to search through the possible space of solutions, and they use stochastic processes to do so. So there's quite a few of the things in this presentation might have already been heard in the last few, but certainly the main advantage of this approach is that you avoid an exhaustive search for a specific solution, and you end up with a near ideal solution, with the trade-off being that it's less computationally expensive and ideally takes less time. And because of the randomness within the nature of some of these algorithms, sorry about that, within these algorithms, is that you cannot determine specifically the path that the algorithm is going to take. And so given the same inputs, you're not guaranteed the same outputs or the same path. Popular examples of these algorithms are relatively well-known ones: genetic algorithms, evolutionary algorithms, estimation of distribution, and so forth. So when we talk about something like a genetic algorithm, we're talking in terms of trajectories, we're talking about the populations that they create throughout the solving process. So as may have been recognized from a few presentations ago, but if you look at for instance, the checkerboard problem, there are two ideal global solutions here, but you're not guaranteed to get any one specific one when you run a genetic algorithm, for instance, because you can't determine specifically where that path is going to be. But as it goes through the process, each step that it goes through, each generation, it is collecting knowledge without any prior source of it about the problem structure itself, and that is represented in the populations as it solves the problem itself. And it is possible at that point to derive an explanation to an end user, but it can often be very difficult or overly complex for them to understand without prior knowledge of the system itself and a lot of the methods involved. And this is a growing issue, especially with non-deterministic algorithms or just complex black box systems being used more and more in recent times. Specifically, if I give some examples here, then used for timetabling and production scheduling, you have delivery pickup and scheduling, route calculations, and I've even seen examples where they're being used as set points for continuous manufacturing processes with multiple different inputs and outputs. So as the use of these continues to grow, the need for explanation naturally is going to continue to increase. So it's already been mentioned before in terms of GDPR is a very important part of that. For myself, one of the early entry points here is a 2019 and 2020 collection of papers and reviews about black box in medicine and the need for transparency. And that is also echoed specifically in peeking inside the black box ART principles, which I come across. And again, these have been mentioned today about accountability, responsibility, and transparency. We've been covering quite a bit of detail, but you can see a running theme here in which these things really need to be taken into account when you're creating an explanation, and it can often be difficult with black box systems. Again, as mentioned earlier today, but I guess one of the downsides to going last is that if you take an example such as line, these can be used to take in this case, the coefficients for specific classification problems, and you can use that in a natural language pipeline to generate sentences. So an example here is where that I've given on the screen is that you can create, provided that you have a set list of sentences that you want to use, you can create something along the lines of, in this example, the single greatest contribution to the decision from the variable current account is the value in debt, in debit, and so forth. And the idea here is that you will have context-specific set of language that you want to use, and you have an ability to pluck out statistical values that you can then place in there, whether it be from line, or if another example here is if you're using excuse me, if you're using the Shipley additive explanations or the SHAP values. These can all be used in a natural language situation where you can create sentences and very short paragraphs that might be relatively useful to the end user, and they're going to be context specific. And again, these are helping build trust with the end user as to why a decision has been made. So when we look at specifically algorithm trajectories as a source of these statistics and this ability to pull out values, what we're really talking about here, as I said, is with population-based algorithms, you have a record of the implicit knowledge gained throughout the entire journey of the optimization process. So each path that it goes through, if it's following a highest fitness path, for instance, there are decision points that are being recorded in these populations, and these can be seen through whether or not population diversity is going to change and so forth. And so ideally, as mentioned here, the algorithm will converge on an optimal or near optimal solution, with the trade-off being near optimal, but the benefits being that it is not an exhaustive search of the space. And when the run is complete, you have this trajectory, ideally, which, as I said, has been generated for every run and then recorded. So potentially what you can do here is, if you have trajectories, they have the potential to provide the end user with a source of new explanations, or a source of new statistical values that you can use to build an explanation. So these could be potentially mined. You can look at, if you have multiple runs, you can look at common occurrences or differences between the paths taken by each one algorithm, multiple algorithms. You can look at population diversity metrics. And I have an example here for particle swarms about population diversity metrics being used to determine the exact phase transition point between the exploration and the exploitation phase of a population-based system, so that you can tell when the sudden rate of change happens for diversification in a population. You know that something important has been found there. An important part of the problem has been solved, or at least on that run. And I want to briefly talk about more recently. In fact, very recently, there has been released the search trajectory networks, which has specifically been designed to work on algorithm trajectories themselves. And the idea here is to help create an explanation through the visualization and the analysis of the trajectories taken by multiple different algorithms on benchmark problems. And as you can see here, it's a way of visualizing the path they take over the problem space. And while it's not specifically within the form of an explanation, it certainly can help prop up an explanation by presenting to the end user a visual aid as to why the specific results that were given to them or arrived at, what path it was taken, and potentially why a path wasn't taken. Can be taken from these search trajectory networks. So very briefly, in conclusion, this is an area that I very recently moved into for my own PhD research, and I feel that non-deterministic algorithms, their use in industry is continually increasing, and is set to do so in the future. And the use of natural language generation is going to be key in being able to convert a lot of these raw statistical pieces that you can extract from trajectories of algorithms into end user, more friendly, understandable sentences, and they're going to be domain specific. And because of that, I feel like the trajectories are an important feature, and they can, excuse me, they can be mined for more valuable information in regards to explanation, whether it be the generation of an explanation itself or simply to support and prop up a previous explanation from another system, as we've seen from the likes of Line and so forth. Sorry, and thank you very much.
Oh, thank you, Martin, for that presentation. I think we have good time for questions, and if you have any question, please indicate. Any questions? Okay, I'll have one from Cyprian. You can go ahead.
Hi, Martin. I have a really simple question. So, chronologically speaking, what would you say are the biggest developments that are, how should I say, should be taken into consideration when looking into how trajectory mining can improve the acceptance or at least the explainability of population-based meta-heuristics?
Certainly. So I think if we start working most recently to backwards, as the example that I give in there of the search trajectory networks is an excellent way of supporting an explanation, because you now have a visual way of comparing different algorithms and their path through the search space. And I think if you were to move it slowly backwards, so there has been work, and this is very closely related, what I'm looking at, to the likes of surrogate modeling and so forth, where you can have Markov field network models to help generate an explanation. So I think if you were to start moving backwards to that, one of the things that I'm personally looking at is closer to the population diversity metrics. Again, I'd had an example there, but I can unfortunately stop sharing my screen. But that's one of the things that I'm specifically looking at, is that phase transition between the exploration phase and then the exploitation phase in populations. And the concept that I'm hoping to look further into is that when that happens over multiple runs, if you have different starting points within a search, you can then compare when that sudden rate of change happens. So then you can try and see whether or not there is a specific group or clique of variables and variable values that seems to trigger that sudden state change, and if it's common between different runs.
Thank you very much.
Yeah, thanks for that, Sylvain. Kyle, yes, go ahead.
When you have to default to manual hand holding, that's when you know. That's when you know you've reached the end of Zoom functionality. No, thank you very much for that interesting insight, Martin. What I'm interested to know is whether possibly a simple question, because maybe I've misconstrued something along the lines of, but to me it seems like trajectory mining presents an opportunity to either explain after the problem has been solved or to explain as the problem is being solved. Is this correct? What are your thoughts on that?
Yes, I may have forgotten to cover that in the presentation, apologies, but this is very much a post hoc approach to it. So the algorithm has already been run, you already have your trajectories being having been generated from an algorithm run, and this is to help explain why the algorithm took that path rather than as it happens.
Okay, so I understand, but let's say we got to a point like in a genetic algorithm where you've created a number of populations, so on and so forth. Could you then just look at, okay, we won't have knowledge of what trajectories are upcoming, but we might have knowledge of what trajectories led us to this point in the population, which may equip us to say something about how good, how explainable or how good the algorithm is right now. We won't have knowledge of where it gets to, but it could create an opportunity to, I don't know, if you were 2/3 of the way through a run, explain some of your decision making or something like that.
Yes, absolutely. As I said, the approach that I've been looking at the moment is that the trajectory or all the populations have already been generated, that there's nothing stopping you from, instead of trying to create an explanation for the entire trajectory, but to break it into parts, whether or not you decide, as I'd said as an example, when you detect that the population diversity takes a sudden change in value, then that could be an important benchmark that you take up until that point to generate an explanation. And then, as you said, you move forward from that point on to create a separate explanation.
Yeah. Okay. Thank you very much.
Thanks, Kyle. I have a quick one. NDAs being non-deterministic, we pose unique challenges, regarding generating explanations. So, do you think that would affect or how do you think that would affect the explanations if, say, between runs, you end up, or could you end up with different explanations since the populations would differ between different runs?
Yes, absolutely. In fact, that's most likely what's going to happen with a non-deterministic algorithm, is you're probably going to have a different path with every run. So ideally what you were doing is taking multiple runs or multiple trajectories and then trying to find the common points between them for an explanation, rather than one individual run which may have taken a slightly different path than the others. Also to that is that if you find that one specific run has taken a wildly different path, or the explanations that are generated are very different from the average ones that you've generated over multiple different runs, then again, that tells you something about that one specific run, and potentially there's something important about that you can use.
Thanks for that. I think that's the end of this session, and hand over to Kyle to continue with the next event. Thanks, Martin. Over to you, Kyle.